So this project started back in 2015, and I received a phone call from Miras, and they said, would you like to come in and talk to us about this unique project they have? And I went along to a meeting and they presented this very wonderful elliptical wild shape of a building, and of course that was the start of a number of months and years of design for Buro Happold. But actually the story starts for everybody and for today's conversation of the complication and the challenges of the building. The day that our architect Sean Killer of Killer Design sat in a quiet room one day and came up with that wonderful shape which won him the competition and then the appointment of the project. And of course the moment that he did that, and the moment that the client, the Prime Minister's office, selected that building shape, it began a sequence of events triggering the need for the design team to respond to all those challenges that come with the complication of building that shape and making what we say, making the client's vision viable, making the engineering such that we can achieve building what you see out on site today. Well, we all had a lot of fun looking at that wonderful shape and immediately just throwing around some equally wild ideas about how to come up with, I guess, all the key package point solutions. So structures, MEP and facades are always the three core disciplines that feature so heavily on the building given the shape. Starting with the need for of course, the structural solution. I guess at the moment that has the stage, the public stage, because everybody can see it on site. The coming up with a diagrid as the real clever solution of how to form that shape and respond to all of the design challenges and all the client brief requirements. The piece of work for Buro Happold on engineering that diagrid has been dominant throughout the number of years that we carried out the design. When we look at that shape and we're trying to come up with an idea of how to provide structural support to it, in the very early stages we would just take the surface model, if you like, and run it in an analysis environment and see how the shape responds in terms of the loads that are imposed on it. It's an obvious analogy of the structural form of an egg. So we're dealing with, in the very early days, with just a pure shell structure. And from that we can see how the forces move and flow around the surface of the shell, and how the sort of unusual asymmetric shape responds, how the opening squashes, and all of the stress peaks and behaviours that we observe from doing that. Now, once we have an understanding of that, of course we want to think about actually what will the structural form be. Could it be a shell? We explored in early days of perhaps using a concrete shell to mimic that early structural assimilation. Concrete shell, very difficult to do, so we then quickly discount that and then move towards a steelwork solution. Now, for steelwork to be viable, we begin to take away material from that shell structure. So we take away material that isn't working particularly hard on the surface of the shell, and lo and behold, what you actually begin to move towards is the diagrid shape that you see. So here we then begin to arrive at diagrid solutions, numerous structural members in the form, in our case, of diamonds. There are of course other forms, you can use triangular or even just square. And again, in the early stages we arrived at a rough and ready diagrid. And then the fun and all of the good stuff starts, because once we have an outline concept structural solution, the diagrid that we have a good feel has a potential to be efficient and buildable, so we're thinking already about what BAM would ultimately have to deal with. We then have to explore all of the infinite possibilities of what the diagrid geometry could be. Now, the diagrid, if you like, could be anything in the two bookend ranges. It could be many hundreds of thousands of tiny little members, steelwork members, or the exact opposite of that. We could have much longer members which are much bigger. we can have a whole different range of structural size members. So to move that challenge on, we after looking at some bookend scenarios and some rough mock-ups of what that diagram should be, we then began an exercise of scripting out some analysis algorithms which allow us to explore in a computational sense many hundreds of variations of the diagram geometry that you couldn't ordinarily analyse with just a manual method. You would need too many people and it would take you too long.
It sounds like this would be something suitable for AI to automate the testing of different...
Indeed, and it's not dissimilar to that. So we set up a computational model which has some parametric scripting involved in it, and that from an AI perspective, from that setup does what it wants to do and will blindly then spit out all the results that we're after. And what that piece of AI work will do is then tell us actually solution number 27 of the many thousands of solutions that it's run hits the peak of efficiencies and is closest to the criteria that you've set. So for us, we're interested in making members which are all of the same size. So we could have chosen that we have lots of different size members. So we could have had 1,000mm tubes at the base where you have very high forces, and skinny, small 200mm members at the top where the forces are less. But we knew early on that there would be efficiencies in not only cost but fabrication for BAM and Vicendy, in sourcing the material to have a single tube size, all of the logistics of fabrication for Vicendy, connection design, and also fitting the tube sizes consistently into the thickness of the facade that we have. So that for us was a critical criteria that we want to achieve, to have this very unusual shape structurally supported by only one single member size.
Is there any practical reason to have this shape, or is it just to push the limits of human achievement?
Yeah, the shape does a number of things really. Of course, I guess top of the list, it is that wonderful wow factor landmark, and providing Dubai yet again with a world first of a building which is of this shape, and yet it fits in the site in a very particular manner. So the shape complements what we have, the very futuristic for their time, two triangular jet towers. This form is of great contrast to that, and provides the overall site with that continuation of bold, dramatic architectural shapes. Building form.
Technologies are you using in terms of software and how to apply it in the project?
There's a lot of scripting, computational work in the background that's been required to just solve some of the problems that have come up. And that's been created outside of the norms of established software that we're all buying off the shelf and using. When we use all those pieces of software, putting the results back into the more standard type of software to enable us to produce the digital information to allow it to be drawn, the 2D drawings, if you like, are perhaps the traditional end result. And whilst we do have 2D drawings as a byproduct of the modelling, really this project has practically done away with that, and we're working entirely in a digital environment. So the BIM piece of the project, and of course BIM is almost common language now for most projects around the world, but BIM for this project has almost been a necessity to allow us to even build. I think it wouldn't be possible in its current form. I think arriving at some of the design solutions, they would have been different. You wouldn't have realised the efficiencies in both cost. I mean, all the good stuff, all the classics that are key for any client of cost, risk and time are addressed to a much fuller and comprehensive level of rigour through the use of BIM than they could have been done otherwise. So trying to think very early on about design solutions and how that will translate for BAM as the contractor to make things more buildable. Again, the Diagrid has been a good example of that, and we haven't yet talked about the facade. That is the other primary and arguably even a greater challenge than the Diagrid. So the facade itself, the design solutions of that, where we've used a very large panel size to reduce the overall number of lifts, as you can imagine, to clad the building. For this sort of geometry, every single lift you're doing is a different lift. So we have 1,046, by the last count, number of facade panels.
1,046.
And each one of those panels is entirely unique in terms of geometry. Whilst the building is symmetrical front to back, as you look at the model, the calligraphy shapes, the calligraphy are all glazed. Yeah, the calligraphy story began very early on because it was part of Sean Killer's original vision, that he would have calligraphy on the building that would be inspired by a poem from His Highness Sheikh Mohammed. And of course that's an absolutely key architectural aspect of the building. So we knew from day one that we were going to have to address the challenge of making these glazed shapes follow the calligraphy. So one of the early stories again of the Diagrid was that the Diagrid, we made it a particular density so it wouldn't obstruct too many of the windows. Now, whilst the Diagrid will be read through the glazing, and part of the architectural appeal is that during the night time you can see the Diagrid and it'll be quite an interesting feature of the look. Of course, with the MEP, we don't want to be seeing ducts and cable trays and everything else passing through the windows. So from that you could immediately imagine the distribution challenges which all of the MEP has to undergo to dance around all of the calligraphy, to move all of the ducting and cable trays and everything else throughout the building. So the interaction of the position of the calligraphy, the size of the calligraphy, the design and related position of all the MEP has been a huge design undertaking. And again, to even enable us to draw it in 3D has been a mountain to climb. And again, BIM and some of the drafting tools that enable us to do that have been absolutely critical in achieving it. We've had to work very hard to look at the MEP systems, of course the amount of glazing and the shape of the glazing that's on the building. So lots of energy modelling where we've had to introduce the calligraphy in detail and also refine the extent of glazing. So for us, the width of the glazing panels, whether the physical calligraphy script is fatter or thinner aesthetically, also directly drives the amount of glazing area we have, and then in turn the amount of heat gain that the building sees. We're also looking at other energy systems across the building and the wider project. We have a photovoltaic farm that's designated for the project, and all of those components, together with the energy efficiency that's been built into the design, are allowing us to hit LEED Platinum.
So how do you clean the building?
Our stainless steel facade, and that stainless steel finish, which you'll all see in due course, has a particular sheen level to it that we've specified, and has a dimpled surface. And of course, we're keen that always looks pristine. Cleaning any building is always a challenge. You'll see, of course, around town the building management units, the BMUs, the cradles, the cranes that hang over the side of our tall buildings around the city, and either people are working in cradles or hanging off ropes. So to do that on this building is of course a challenge, and the model behind us actually is one of a number of models where we've, and it's funny because we often talk about lots of technology. For the BMU we started, and we still do, putting pins on a foam model of trying to work out where we will have anchor points, belay points for the rope access system. So the building will be cleaned by rope access. We could have had some elaborate cradles and deploying crane systems that we've looked at in the early concept stages, but they of course rather impact the aesthetic of the building and detract quite a lot of floor area. Roughly speaking, the red pins on the top and the underside delineate the rail system that we're using. The blues are the primary anchors, and the greens are the anchors that we're using for the top area, which have their own set of aesthetic requirements, because here we have a viewing deck that you'll be able to go out and look. So we don't want some very unsightly anchors on the facade. And of course then all the anchors are fed into the facade design. So we have some very tricky detailing of the facade panels and attachments through to the steelwork to support the loads that come from the rope access system. The two key areas of fire safety, so analysing the smoke paths and also the evacuation scenarios. So we on both those counts we've employed our own set of performance-based design, given the unusual shape of the building. Trying to apply standardised codes of practice is of course very difficult. So we've used some analysis modelling for the CFD modelling of the smoke evacuation, for the smoke extract. We have a very large atrium again, which is all unique geometries. And then we've used an in-house system for the modelling, the physical modelling, the simulation of people evacuating the building. So we're looking at the next 2 months to close the steelwork, and of course that's a very critical time for us in terms of the level of complication of the steelwork. So comparatively, we've joked internally that we've done the easy bit, which of course it's not, but the closing of the bridge at the top, by virtue of the need to cantilever the two sides and the sensitivity that the diagrid has to movements and tolerances during that process are much higher than the rest of the diagrid. So that closing piece is a lot more complicated and hence takes a little bit more time to complete. But we're hoping to see it finished, bring the two ends together and have the full torus shape completed over the next 2 months.